Good morning, and thanks the organizing committee for inviting me to this wonderful forum. This is a talk on nanotechnology. In fact, to this just to remind you where we are in this endeavor. But coming back to what I'm going to talk about, this will be the fundamental science behind many nanotechnological phenomena were applied to chemical systems, in particular to molecular junctions. I'll describe in a moment. I want to thank two collaborators. We had many of this adventure. Mark Ratner, who could not be here, and Misha Galperin, who is in fact here. What I'm going to do today is to describe these three phenomena: charge transport, heat transport, and light transport in nanoscale, in molecular junctions. To remind us all, although this field that is called molecular electronics, describing charge transport through molecules in nanojunctions, started only maybe 30 years ago, it is all comes on the heels of the old effort on electron transfer, culminated by Marcus theory, including Hash and Jortner, which basically describe the way electrons move from donor to acceptor under the influence of response of the solvent around it, going to the major prediction of electron transfer rate as a function of the driving force, leading to the Nobel Prize by Marcus in 1992. Now, molecular electronics started by putting the molecule first conceptually, then experimentally between two metals and measuring the electron transmission properties of such a device. The basic theory there is Landau theory, which in fact disregards the environmental response, just looking at tunneling of electrons between two metals. The two metals are characterized by these Fermi functions, Fermi populations on the left and on the right. This is where the bias potential enters, and the transmission probability of electron through the molecule. The difference between two Fermi energies is just a function that looks like this. The width is the potential bias between the right and the left. Transmission function reflects the molecular spectroscopy, so if there is one molecular level, there will be one peak. To see current, you need overlap between the two. Experimentally, you achieve it either when you push the molecular level between the two Fermi populations on the right and on the left, or else you can increase the bias. In either case, as a function of the bias or the gate potential, you see a step in the current. You take derivative, you see a peak in the conduction. You go to the lab, and that's what you measure. This is the current, and this is the conduction. And these peaks reflects the molecular peaks, the molecular states. And the fact that you see different lines here also reflects the fact that when you do single molecule experiments, there is noise. Each experiment represents a little bit different configuration than the other. So there is always noise, and I will come back to this a little bit later. So we discussed two phenomena, electron transfer and electron transmission. And then you go to theory, you can relate them to each other basically by eliminating all the factors that has to do with the coupling of the system to the boundaries. Electron transfer, there is donor and acceptor. Electron transmission, there are two metals on the left and the right. Other than that, the transmission through the molecule again is common. And this is what is expressed by this expression, which you can verify this, has been verified experimentally up to, of course, this is very simple theory, up to error. So this is where we are. We put molecules between metals. We look at what happens. I mentioned at the beginning that we are looking at electron transport, but also heat phenomena and light phenomena in such nanosystems. And I could center this talk about any of them. I choose to do it to center it around electron transfer, but in fact we could go to light or to heat and do the same. And I will give you some examples later. Also, I want to remind us that we are now in the post-hype period of this field, molecular electronics. If you went back some 20 years, you will see a lot of expectations, industrial expectations coming out of this field. Makes you remember this article by Rolf Landauer, which is the theoretical father of electronic transport in nanojunctions. Basically, it tells you that fields where you invent some new concept and you demonstrate it in the laboratories, on the way to applications also go, not always, but many times go to a period of hypes where the expectations exceed the achievements. Landauer gives several examples of fields that went through this era. The good news is that all these subjects are now back in force and other way to real applications. So I believe molecular electronics is going there in the same way. If we are going there, if we are going to use molecular electronics applications, this is what we want to do. We want to first control the fabrication of such molecular junctions. We want to understand their stabilities. Characterization means that we are looking at a nanosystem. We put molecules there, how the molecules look like, how they sit, how they connect, are they there at all, are questions that we have to clarify. Functionality, we want to do something about the system, and we want to control their properties and their response. Now, as a theoretician, this is how I construct the system. This is the system that we are going to study. In addition to this, that is electron transport between two metals on the left and on the right. These are all the molecular degrees of freedom, but there is possibility to put light on the system, and you have to consider thermal effects, heat generation, heat dissipation during the operation. And as I said, I could put either one of these phenomena, lighting junctions or heat transporting junctions, at the center of such a talk. Like if you focusing on light, what do we have in nanostructure systems? First, we have what we call the lightning rod effect, which is the equivalent in nano-size systems to the usual lightning rod, basically telling you that the topography of the metal structures can affect the local field and therefore the response of the system near such topological features. And of course, in metal junctions and semiconductor junctions, this can many times be the case. Then there is what is known in electrostatics as the image effect. You put charge on one side of a metal or a semiconductor, you see the image of this side on the other, and a system, say a molecule here, will respond to both the charge and its image. Image is just a manifestation of the polarization of the metal surface or the semiconductor surface due to the real charge on the other side. And there are plasmons. Plasmons are collective motions of electrons in metal, nano-size metal systems, also on metal surfaces. You probably saw this many times. One way to see the topological structure properties effect of plasmons is to realize that the same kind of excitations, collective motions of electrons in nanostructures, give rise to different spectroscopy just depending on the size of this kind of particles. If this was a talk on plasmons only, I would expand on actually applications. This is not hype anymore. This is actually part of ongoing research to describe the local heating that is affected by exciting plasmon in particles in what is called phototherapy today. Another applications of plasmon. In fact, when we started to work on this in a different context some 30 years ago, I was on sabbatical in Bell Laboratories, and Bell Laboratories, every time you have an idea, somebody asks, is it patented? This one was at least conceptually, so we issued a patent on the possibilities to use plasmons in photochemistry. And This patent was issued in 1984. 17 years passed without real demonstration of this, but today you see, in fact, a lot of activity in plasmon-induced photochemistry of many. This is just one example. There are many experimental demonstrations now. Going to heat, heat was the third transport phenomena I was referring to. So you can simply look at heat transport in junctions in the same way that you look at electron transport in junctions. In fact, this is the first experiment that I'm familiar with people actually measure heat through molecular layers between two heat reservoirs, if you want. This is just over 10 years ago. I will come back to heat transport. Actually, this is still results of heat transport. This is the heat conduction by molecules, demonstrating again a sort of interesting observations that the heat conduction does not depend on molecular on molecular length, as you see here. I will not go into details about that. But look at all these titles. This is what I would talk about if this was just a talk about heat transport. So you see heat transport through atomic contacts, quantum of thermal conductance, thermal rectifier, thermoelectricity in molecular junctions, heat transistors. So there are many interesting subjects in this transport phenomenon alone. But let's go back to molecular electronics. And what I want to do today in the rest of my talk, given the time, is not telling you more about present-day research, but telling you about challenges, as our chairman asked us, is to focus on challenges. So I want to go quickly through a list of open issues in the field, or what is difficult, what is expected from us on the way to applications. And the first problem that I would say in this field of charge transport in molecular junctions is the fact that, as I already showed you before, noise is a prominent part of the response of the system just because there are so few, sometimes just one molecule in the junction. So if you go to a typical experimental result today, they will not tell you what is the conduction of a given molecular junction. They will give you a histogram. They do thousands of experiments. This is the probability to see a particular charge in this type of experiments. So you see a lot of information here. There is this conduction and this conduction. There are peaks, but the conduction can come to be anything in this range. And it is beautiful science, and you can get a lot of insight from that, but you do not want your cell phone to operate on a histogram type, to have a histogram type behavior. So this, I would say, is one major barrier between us and applications of single or few molecule junctions. Computational challenges. If you are theoreticians trying to compute properties of these systems, the computations are challenging for many reasons. One of them is that we are doing quantum chemistry in an open system. Even the number of electrons is not given in such a calculations. But I want to focus on this generic difficulty of having to address many timescales. All this sort of, if you want, a list of interesting timescales in chemical systems, and all of them can kind to be expressed in the response of a molecular junctions. Usually we focus on a few of them, but many times we see the results of many of them interacting together. And so this makes it, of course, very interesting. Physically, of course, you know that, say, the outcome of these experiments will depend on how fast this bird is running relative to the response of the water on which it is running. But computationally, if we try to compute something which has so many different timescales, you can realize this can be very difficult. So this is another barrier on ways to understanding this system. And of course, this is an ongoing research, ongoing effort, not only in this field, in every field of computational science, to bridge between different timescales in the calculation. Heat transport I already mentioned. When we think of this in the context of molecular junctions. Sorry, I think I went too fast. Before heat transport, nonlinearity and multistability. This has to do also with the competition, in fact, the quantum analog of this phenomenon, competition between transport and localization. And to show you the experimental manifestations first of this kind of competition, here are several examples of nonlinear behavior in molecular conduction. You see current, all of them show current as a function of voltage. You see here negative differential resistance, where the current goes down when we increase the voltage above some threshold. You see hysteresis phenomena, where when we increase the voltage, we see some current, we decrease it, you see another one. All of them are manifestations of the different time scales and the competition between localization and transport in these junctions. Theoretically, when you try to compute these things, some of the orbitals between the two metals are delocalized, some are localized where electrons can be localized. If you can address all these different time scales, then you can see theoretically the same phenomena I showed you before. What else? Heat conduction, I come back here. Heat conduction are behind the need to stabilize molecular junctions. When we pass current through molecules, heat is generated. It has to be dissipated for the junctions to be stable. But we can study it for its own right. I can put, this is alkane molecule between two hot and cold reservoirs. You can simulate the heat conduction in this in such a junction as a function of molecular length. This was done in 2003. There were no experiments at that time. Experiments came up. I will not have time to tell you about details of some of them, but let me just show you. If you look at these simulations, you can compare it to this kind of recent experiment, which you see very similar behavior in the junctions. Again, thermal conduction as a function of length of an alkane chain between a hot and cold reservoir. Next, to learn how to use light in these junctions, I told you about what light can do. To couple this with molecular conduction is an ongoing research with a lot of promise. A recent example, we put light on junctions. We have to address the possibilities that plasmons will participate, but this is what you can do with light in junctions. This is a molecule between two graphene electrodes, and these are experimental results obtained from the group of Sufeng Guo in Beijing. This is the conduction or the current as a function of time, where with UV light you can switch between almost insulating to conducting form of this molecule, and then with visible light you can go back, and you can do it for a long time in many switch on and switch off phenomena. So light can be used to control these junctions. Light can be used to study the response, to study their structure. I will not have time to tell you about that. But basically to control light together with the heat it generates and electronic conduction is still a major challenge for many of these junctions. Oops, this is what. Okay, what else? This is a quantum phenomenon. Electrons going through molecules, and there are several passes acting together. You can have constructive interference, you can have destructive interference, you can try to control it and to use it to control the properties of junctions. I have just one example here. So this is actually a theoretical calculation, but the experimental results showing in destructive interference as a function of gate voltage here in a molecular junction is looking very, very similar to this dip in the conduction, and there are many recent experiments over the past 2 or 3 years which demonstrate this kind of interference features in molecular junctions. Magnetic field effects I will not talk about, but let's go to something related, spin selectivity. Here in the Weizmann Institute, my friend Ron Naaman and his group and some collaborators have shown in recent years that when you send electrons through chiral structures, they emerge with their spin orientation preferred in one direction or another, depending on the helicity of these chains. This is an extremely interesting phenomenon. I must say that I do not really understand it, and I'm in a good company of practically everybody else. So if you want, this is the opposite to what was shown to us in the previous talk. There was an experiment where the theoretical explanation was already known and expected. Here there is an experimental phenomenon that people are still struggling to understand. And if proven robust as it appears to be, then it has a future in quite a few applications. The effects are big. You see sometimes 60% preference of one spin over the other in this kind of transmission. And last, we can look at implications of everything I told you about light, heat, and electron conductions in photovoltaic cells, of course, but practically every other kind of energy conversion nano device. And this brings about the current recent interest in what is called quantum thermodynamics, because if we are interested and are able to study both experimentally and theoretically energy conversion, then understanding the efficiency of such processes and their possible realization is a question that brings thermodynamics into light, but now in the quantum regime. And some of what we and others do are studying this kind of phenomena. Like if you want, this is a model for a photovoltaic cell. So what you have here are molecules that can induce charge separation. You have what drives this system is the temperature difference between the ambient system and the sun. But basically, this is the same kind of molecular junction that I showed you before. Now, applying it as an energy conversion device, in this case, converting the temperature difference between the sun and the ambient into voltage in this cell is a thermodynamic problem that people would like to understand better than we do today. And I think I want to end with this, so thank you very much for your attention.
Questions and comments? Yes.
So you presented this very beautiful survey of what are the challenges, for instance, to theoretical computation. I would like to ask you more about connections, so challenges between present day theory and present day experiment in two respects. One is, look, for macroscopic conduction of electricity, there is a good degree of universal behavior, both experimentally and theoretically. Basically, ohmic behavior is not everything, but it's a lot. Do we have such universal behavior when you transmit charges in molecules? Maybe you showed the result, but I couldn't see such. And the other question is really, what is the level of comparison between theory and experiment, for example, on transmission through molecules?
Okay, let's talk about universality first. It really depends on what you define as universal, because you say Ohm's law is universal, and then you take a semiconductor and you see anything but Ohm's law. So molecules in this sense are universal in the semiconductor sense. Basically, they show you the effect of the existence of a gap between states, which will tell you that there is a threshold in the conduction. But then, again, like in semiconductor devices, molecules are not inert transport media, so their state changes with the boundary conditions, with the voltage, if you want, which is the origin of nonlinear behavior. Like in small voltages, electron will go through. When I change voltage, I change the molecular electronic structure, I can get electron localization that will give rise to what is called negative differential resistance. So all the phenomena that I'm talking about are universal in the sense that they are not properties of one particular molecule, but properties of manifestations of general phenomena that can take place, but there is more than one general phenomenon. Ohm's law is just the competition between transports and collisions, and here we have many more processes that takes place. About agreements between theory and experiments, it is becoming much better. So if you asked me this 10 years ago, I would say that they are okay up to 2 orders of magnitude. And then now I will say they are okay up to a factor of 2. There is a progress.
Yeah.
I was interested in your comments on heat. And so this question may not be very sensible, but I'm curious. We know that through control of dispersion, we can make slow light. Can you, by analogous idea, can you make slow heat?
It's a great question. I did not think of that. I do not see why not, except that we do not have control over the structure. We do not have the phonon equivalence of a photon lattice, at least not so far that I know of. So I do not know how to construct it, but in principle, I do not see a reason why not to try for heat. Everything else that you do with photons, you can do with phonons as well. As I gave you the list, I mean, up to things that you do not know with photons, usually like transistors. But slow phonons is an interesting concept. One should think of
I
that.
think Modi has a comment on that.
I have a comment on that. You know that slow light works on ballistic transport only, not on diffusive transport. In other words, if you try to have scattered light and to try to slow it down, it will not preserve the wave function. It will not preserve the pulse. So it will be meaningless. So if you want to have slow heat, what you need, first of all, to start by having ballistic transport of heat.
The good news is that we have it. That is, in fact, when you take a molecule like this alkane, I showed the experimental results. If you remember, it went up, then it went down, then it became flat. This flat region is, in fact, the ballistic region. Eventually, it should go down with length.
So if you can make a pulse of heat, okay, let's say a pre-designed pulse of heat and show that you can actually propagate it, pulse of heat like this, whatever the response time will be, then you can talk about slowing down heat.
So to show you the difference between what you can do with light and what people can do with heat, the only way people can generate pulse of heat today is to put molecules on a metal surface and just send the pulse of light into the metal, raising the temperature in a step way, and this creates a pulse of heat through the molecules. And such experiments have been done. But this is not a very high quality wave packet that you can generate in photons. But this is the experimental limitations, I think.
So I have a question related to the first one. One of the key missing pieces in molecular electronics was often control experiments. And I think with time we've gotten better at that. So for example, in the connected molecule to the graphene electrodes, there should be an out of molecular resonance or replacement chromophore that doesn't absorb, where one doesn't see those features. Is that a part of that?
First, you're right. In fact, this was this experimental result by the Chinese group that I mentioned. We collaborated with them on the theoretical aspects of these junctions. Later, I heard some criticism from experimental friends that they did not do enough control experiments